So binary exploitation is just like any sort of hacking, any sort of attacking insecurity where you're trying to trick a computer into doing something it shouldn't do, but it's on a lower level. So like whereas with say web hacking, you might be trying to trick a web browser or a web server into doing something it shouldn't, you wouldn't expect it to do or it shouldn't be doing. Here we're tricking a program into doing something it shouldn't be doing, whether it's a user land program like a Discord or a command line program, or heck, it could even be an operating system kernel, tricking the Linux kernel into doing something it shouldn't. Um, so it's just like any other vulnerability, any other type of attack. You're tricking a computer, but it's at a much lower level. And by lower level, I mean you're dealing with things at like say the assembly language level, like the CPU level, where you're thinking you're thinking kind of down there, if that makes sense. Um, so and you've let's see here. I guess what similar to let me start off by saying this. So, binary exploitation, low level security is something I've been interested in for a few years now. And a misconception that I commonly see and commonly experience, that's not in the slides, but this is just kind of a personal aside. People kind of view it as something that's super advanced and super, quote unquote, elite, and really, really hard, right? A lot of people think of it as being, sort of, I guess, harder than other types of security. Or at least that's a sentiment I've seen expressed or kind of feel expressed by some people. And I'm here to tell you that that's not true. I think reversing and binary exploitation can be just as, I don't want to say easy, I'll say just as hard as any other type of security. But I guess in some ways just as easy as well. It's just a different set of knowledge that's required. I think the thing is people see assembly language and people see debuggers and operating systems internals and other low level stuff and they get all scared. And I mean, yeah, I guess that's kind of reasonable. Um, but but all that low level stuff isn't necessarily, it's not as scary as it looks and it's totally doable. Um, so with that in mind, I guess binary exploitation is totally something that people can do because people do it, and just because it's low level doesn't mean it should be scary. Just something to state that I thought was important. Uh, but anyway, yeah. So at a low level, you can trick programs into doing things they shouldn't do. A common example being a program allocates a static amount of memory, but allows you to write more memory than it allocated, and that can have undefined behavior. Usually, that is overwriting subsequent memory you shouldn't be able to overwrite. That's a buffer overflow. Um, that's something a programmer might not consider if they're just writing code that use and just using functions left and right, and they're not really thinking about what they're doing, or they are thinking about what they're doing, but there could just be really tricky undefined behavior, or the language they're using C, sorry, the language they're using doesn't really do a lot of hand holding. It doesn't encourage them to write secure code. uh, and just in the same vein as other areas, say like again web hacking, you have different classes of vulnerabilities. So whereas in web hacking you'd have say cross-site scripting, SQL injection, um, in binary exploitation you also have different types of exploitation. You can do heap-based or stack-based exploitation. You can do integer overflows. You can exploit flaws in the program logic, and I'll get to that in a second. Um, so um, so there's a number of ways you can find vulnerabilities in code. You can read the code. Now, sometimes that's easier said than done. If you have the access to the source code, that's like the best case scenario because you can just read the high level source, which is usually going to be written in say like C, C++, something similar to that. Um, and that's nice because reading a higher level language is always better or easier in most cases than reading something lower level like assembly, which gets to the somewhat worst case scenario, but also oftentimes very common case scenario where you're not given code, you're only given access to an executable file like a binary. So if you want to reverse engineer a video game and maybe you want to find vulnerabilities in the video game, because I don't know, you want to write some sort of cheat program, for example, you, I mean, Bethesda's not going to give you access to their source code for Fallout 76. So they're just going to give you an executable file. So with that executable file, you can't actually read the assembly code. You just have to disassemble it first. but at that point you're still reading assembly, and reading assembly is a lot more tedious. So but it's still doable, and with a lot of additional tools to help you out. A lot of finding vulnerabilities. A lot of finding vulnerabilities is just reverse engineering and playing with the program. And a lot of that is figuring out what parts of the program you care about and what parts of the program you don't care about. Um, uh, you because you're not going to read all of the code for most programs that you're going to reverse out there. You're not going to read all of it. There's too much. So you're just reading certain pieces and trying to narrow down what's important. Um, let's see here. So, um, and again, as I was saying before, good examples of vulnerabilities you might find that are lower level would be an integer overflow, uh, which is where the way integers are represented in binary is you have like say 4 bytes or maybe 8 bytes for a larger integer. But the problem is since you have a fixed amount of space, eventually you're going to run out of bits. And if you have a number that gets too big, it's going to wrap around to zero. So you'll go to from like 4 billion and something to zero. Or if it's a signed integer, the number will get so big that it'll eventually become negative because with two's complement and all, that last bit will be flipped, which indicates it's a negative number. So you can that's one of those things where on its own it's not necessarily a vulnerability you can abuse in and of itself directly. In some cases you can use an flow just by itself and maybe get yourself something, but oftentimes that's something you would combine with something else. uh so one example I can maybe think off the top of my head, just making up an example, would be if you had integer underflow. That's the easiest thing I can come up with, where you make the number smaller and smaller to the point where it gets really large. Maybe you have a negative number that the user has control, and then you exploit that by making that number so small that it actually it gets small enough that the number becomes super big because the most significant bit flips two's complement. uh you know Two's complement it takes effect as it always does, and all of a sudden the number goes from being like negative 4 billion or negative 2 billion or whatever to positive 4 billion or positive, and the fact that it's positive might be important because maybe that number that you're allowed to make small is a number that controls how much memory you're allowed to allocate for something, or how much memory something's allowed to read, how many bytes something's allowed to read. And so that's an example where you could turn a small number. I mean, that's kind of a contrived example and maybe not the best example, but integer overflow, the point is that's like an example. It's a small vulnerability that's usually used as a part to a larger goal, to a larger exploit. So it's usually used as just a step. Um, and accessing array out of bounds. So accessing out of the bounds of an array is dangerous because that could be a vulnerability that allows you to read data you shouldn't be reading. Um, and so that's more of like an arbitrary, potentially a semi-arbitrary read, or just reading. Like, one example I can think of is if you have a stack allocated array, and as we'll see later, let's say that your computer is using protection that places what's called a stack cookie on the stack, essentially just a piece of data, um, that it will later check, and if that data's been changed, then corruption has occurred and crash the program. Someone's trying to hack you, or whatever. Um, let's say uh, let's say you're dealing with stack cookies and you have an array that's allocated on a stack. Reading an array Reading out of bounds of the array, being able to read outside of that array is dangerous, because then you could potentially read that stack cookie. You know what that stack cookie is, and when you want to exploit the program, and let's say we're dealing with a stack based buffer overflow, you want to exploit that. Since you know what that stack cookie is, you can overwrite the value with just that stack cookie value. It doesn't look like the stack cookie's been tampered with, um, and you win. So reading out of bounds can be dangerous. Writing out of bounds can also be dangerous, because then you're writing to memory you shouldn't be writing to, and if that memory is important, well, you can change behavior. And then buffer overflows are great. There's actually more types of buffer overflow than there are just stack. Although stack overflows are what people talk about, I guess, a lot, and what we're probably most familiar with. They're often what you kind of learn about first in binary exploitation. I mean, there's also heap-based overflow. Like, there's also heap exploitation, and with that, you might be able to overflow a buffer on the heap. So that would be like a heap buffer overflow. But there's other types of heap exploitation too, and that's something I'm going to talk about a little bit, but not too much because I'm by no means an expert in exploitation. Um, Not to mention it's usually a little bit more advanced. And actually, I'll get to that in. I'll get to. I'll summarize a little bit of heap exploitation, talk about why it's more later. So, let's see here. Yeah, okay. Um, so again, I'm not quite going 100% in order here, but I hope that's okay. Uh, yeah. So, oh yeah, sorry, my bad. Um, I was just pausing for a bit. Just I lost my train of thought. So,
Not a big deal.
let's see. So, as like the middle bullet of this slide states, you might want different depending on like where you're attacking. That might get you. How do I best phrase this? Um, the target you're attacking is going to have scope, right? So if you're attacking a user space program, and you, let's say you discover a vulnerability in a user space program that allows you to execute arbitrary code, arbitrary code execution, you can now make that user space program uh, run any code you want. But that that user space program is limited by the permissions limited by, so therefore you'll still be limited by those permissions too. So you can exploit, I mean, for example, Discord, and have Discord run all the code at once. But Discord's, not going to be able to necessarily change user passwords because it doesn't have, that kind of permission. It doesn't have that, operating system level. So, um, so depending on what you want to do, or I mean, depending what you're interested in, maybe you want to attack user space programs because that kind of access is, sufficient. Other times, if you say attack operating systems themselves, like the Linux kernel, if you find a vulnerability in the way the Linux kernel handles things, or the Windows NT kernel, or even better, you could target a driver because drivers are pretty great because people update them, and they get changed out oftentimes behind the scenes, and drivers get a lot of some of those operating system level permissions because drivers need a lot of low level access. They need more powerful access than user space programs do for interfacing with hardware. So if you can attack device drivers, um, that's a pretty good target. Um, so keep in mind when you're exploiting, or keep in mind when you're looking for vulnerabilities, or really when you're just picking a target. Different targets are going to give you different permissions. Um, and then finally at the bottom, when it comes to logic, people write code. People aren't always the best at writing code because writing code is hard, and it's possible. I mean, heck, I've written a lot of bad code myself, and I'm sure we all have. Even if you're a good programmer, I mean, if you're writing a really if you're developing for a project and it's really tough, or it's just super complicated and there's a lot of moving parts, and even if other people on your team aren't necessarily as good, um, there's gonna be some inconsistencies, and there's gonna be some weird behavior in the logic, and it could even be, how do I put this? It's okay. I'm gonna be honest with you. Logic related bugs are not something I've dealt with a lot in my, I guess, like, quote unquote exploitation career. I know people who know a lot about like logic bugs. It's not something I'm an expert on, so I can't give the best examples. Um, the most I can say about logic bugs, logic related vulnerabilities, is you're not taking advantage of memory corruption. You're not taking advantage of that sort of thing. You're more so taking advantage of the structure of the program, uh, and it's, you're taking advantage of the rules of the program, the structure of the program, and it technically allows you to do something that the programmer would not have intended, but like, the way that, say, a bunch of if then statements are ordered, or the way like you have these nested loops that interact with each other. Like the way that things just are kind of structured, you can get things to happen. But it's not like you're overwriting data. It's not like you're flipping an integer to be negative to positive or something like that. It's more it's almost like you're debating the program and you're arguing with it, and since you're arguing with pure rationality, with pure logic, you get the program to concede something it would otherwise not concede. uh, so it's kind of like, my understanding is that's kind of how that works. Analyzing, let's see, so code analysis. Yes, this is where you start getting into a little bit of reverse engineering. um, And a quick aside on that, so you could almost sort of view reverse engineering and binary exploitation as two sides to the same coin, sort of. There are a lot of cases where you want to exploit it, because all in all, reverse engineering is just taking something to figure out how it works, and it's very reasonable that you want to take something apart, figure out how it works, and that's it. You don't want to do anything else with it. You're just curious. Oh, how does this work? What formulas is this program using? How does it calculate these values? And that might just be all you want to know. Um, with binary exploitation, though, you typically do need to, in order to do exploitation. And oftentimes, a goal of reversing is to learn about the program so that you can check it. So they're oftentimes two sides of the same coin. Um, if you want to screw with something, you gotta know kind of how it works, and if you works, that'll enable you to screw with it, sort of. Um, so yeah, how do you reverse engineer a program? Well, you have static analysis, and those are just fancy terms for, you can look at a program without actually running the program, just by either reading the code or reading attributes of the executable file, or just kind of looking at what you're given. That's static analysis. You don't run the code, you just kind of you know you look at it, you read it. And then dynamic analysis is, yeah, you run the code. So you can code and does. You could run it with some tools and have those tools analyze if it writes files, or if it reads from files, or if it opens up network connections, or if it does anything else. Or you could run code under a debugger, and that's a great way to do dynamic analysis, because if you run code under a debugger, you can start and stop. You can like start and stop, and then start again, and you breakpoints, which allow you to run code up to a certain point. You can tinker with memory and register values and change state as you're running the program, so you can see how those state changes change how the program runs. And that's cool, because you might be thinking, if I could write to this byte, I could get this thing to happen, but I don't know how to write to this byte yet. But let's pretend I can write to this byte. And then you change that byte in the debugger, you run the program, and you confirm your hypothesis and say, okay, I could make that happen. And then at that point, maybe the goal of exploitation is getting to write to that byte, because if you write to that byte, then you can prove you can get to this other place. So debuggers are great. I love them. Specifically GDB, since I've done more Linux binary exploitation, and GDB is pretty great. But really, any debugger that allows you to modify memory and register values is going to be very useful. Yeah. Oh yes, trying to figure out what inputs you control, and I read that line verbatim for a reason. I want to emphasize that, because like, computers are great, but part of what makes them useful is the fact that um, they take in user input, and that might seem pretty obvious, but like, the whole idea is a computer can do computation, but it's kind of a rock unless uh, people are giving it stuff to do. And that could be, maybe you type in input at a console, at a terminal. It could be, but user input is more than just that. User input's a bit more abstract. User input is anything that a person puts into the computer, directly or indirectly, that the computer ends up using for computation. So that could be type on a keyboard, could be mouse movement, could be a microphone, or could be a file, just a file itself. Because if a program reads from a file, that file is input to the program, and a person could write to that file. So what I'm saying here is, user input's not necessarily type input to a program on your keyboard. User input could be you stream a bunch of TCP packets with corrupted data in them to a vulnerable service on your computer. In this case, like a network stream, right? Or it could be a file, in that maybe the program reads from a configuration file, but you can kind of tweak the configuration file and do some tricky stuff with it, where if the doesn't read that config file safely, you can get stuff to happen. So in that case, just a text file or any other type of file could be user input. So user input, it helps to think outside of the box. Think, what all does this program read or take in that's not necessarily just my mouse movement and my keyboard? Because that could, that could be a vector for attack. Um, yeah, consider what inputs the program takes in, uh, and uh, and that's a good way to think outside of the box too. And I talked a little bit about. Okay, I already talked about some of this. Um, so um, so this, I guess, so the slide here classifies. Um, I guess I haven't seen those terms used before in dynamic analysis. Um, so again, static analysis is, doing everything you can to analyze the program, that's not running it. That doesn't have to do with actually running the code. So reading the code, disassembling it, looking at the executable, just looking at attributes of the program, or reading the code of the program. That's pretty much static analysis. Again, dynamic analysis is anything that has to do fuzzing. Fuzzing is pretty lit, and I haven't done a lot of it, but I was introduced to it a bit from Stuart, and I've talked to some other people about it, and it's very useful. Fuzzing is essentially feeding a bunch of weird inputs to the program, sort of force feeding a program with a bunch of weird inputs to see if any of those um and you can do kind of naive fuzzing where program and seeing if any of those cause crash or weird behavior, and then if any of those inputs do, you figure out which input caused the trip, which input caused the crash, the weird behavior, and you figure out why, and then maybe that's a bug, maybe that's a vulnerability. And then you can do smarter fuzzing, where you're fuzzing a program with inputs that are more realistic, but maybe randomly generated or generated a algorithm. So you can do like intelligent and unintelligent fuzzing, but fuzzing's pretty cool. It's almost like a brute force way of finding bugs and vulnerabilities, and it's not just good for finding. It's honestly, it's just good for finding bugs. It's a technique that's been talked about, a lot in the security world, but also has some real power to just developers who want to make systems more stable and less buggy. Um, and Yeah, that's actually a pretty fun point that I hadn't considered, but is actually probably worth mentioning. So with static analysis, and then the little sub bullet there, sometimes just compiling with dash wall and looking at warnings can help. Yeah, so um, if you have access to the program source code, meaning you can, and you can compile it from source. If you if you make and compile a program from source, and maybe add, tack on some flags to the compiler options that maybe check for extra types of errors. Maybe you'll get a bunch of warnings that you wouldn't have gotten in. Those will give you some hints as to where to look. So yeah, that's another thing you can do. Um, but yeah, and I guess I'm going out of order. But yeah, going back up, manual. Um, of course, reading code. If you know what you're looking for and you know how vulnerabilities work, you can read code and maybe spot a potential vulnerability. Maybe you spot that there's an array that has, that allocates space for 20 bytes, and you notice a call to gets, and you think, gets doesn't do bounds checking, and that's an obvious one. Like gets is one of those things where once you know that gets is bad and why, you'll never not see it. But you don't really see gets in the wild anymore. Usually, you might see like an f gets, or you might see a scan, maybe not a scanf, you'd see maybe whatever version of, I think, you'll see other, like, it's usually gonna be more subtle than that, but I guess still, that the idea there is just you're and you're trying to notice patterns and, possibilities that for things that are a little bit sketch, or you know that might I mean, it's just reading code. I say it like it's easy. It's not. It can take a lot of time. But a lot of these, of course, a lot of these strategies for finding vulnerabilities, you combine with, with one another. So I'll find myself reading code in using a disassembler to read the assembly code for a function that I think might be vulnerable, and at the same time I'll have another terminal open and I'm debugging the program. And then I have another terminal where I can just run it as normal, and I'll be doing a number of things at the same time. So you can combine a lot, and in fact, you oftentimes do. Okay, so again, we have different types of vulnerabilities with binary exploitation. I talked a bit about integer overflows. I keep hinting at buffer, um, and you have uninitialized memory disclosure. I haven't seen it referred to as that exactly, but that's kind of that's sort of a that can be a part of some other vulnerabilities. So there can be vulnerabilities where you what is it? You initialize, but you don't. There can be vulnerabilities where you say there's no right to it yet, but that memory hasn't been zeroed out, and so it still has whatever old values it had. And if you can read to a variable before it's been, if you can read from a variable before it's been written to, you can maybe read old memory, um, and maybe that's not useful. Maybe it's garbage, but maybe that old memory is useful, and that's one of those things where it really depends on the case. I would say, at least from what I can think of, you might see some stuff like that with exploitation. Um, like say use after free is kind of like that sort of, except for you're initializing the memory yourself and then you're freeing it, and then that memory's um after the free when it shouldn't be. I'm getting ahead of myself, but yeah. So uninitialized memory disclosure, reading from memory that hasn't been written to yet, but might have an older value that's useful, that's already that's still there. Printf, oh boy. Format string attacks they're kind of silly. They're very silly, and they don't just apply to printf. I mean, they apply to, well, fprintf as well. I think they can also apply to scanf. And there's some other functions I'm forgetting right now, but that also take in format string that people don't necessarily think of, but that can potentially be vulnerable to. Printf as a function is usually the example. But there are other functions that use too. Um, so yeah. Oh, okay, cool. Wait, what did you say again? Sorry, something about Discord.
The connection dropped for a second, and we didn't hear that last point you
Oh,
made about
oh, okay,
printf.
about printf.
Yep.
Oh, okay, sorry, yeah. So anyways, the moral of the story there, with what I was saying before, was just that printf as a function is when you're talking about format string vulnerabilities, everyone always talks about printf, and printf is like the best function to study and learn about when you're looking into this stuff, when you're learning about it. But there are other functions out there that also use format strings, and format string attacks are less about printf specifically or other functions specifically, and they're more about just using format strings themselves uh, incorrectly. So you can get creative with that. I've seen some creative. But anyways, back to what a format string attack is. So as you'll see here in the sub bullet, never do printf user input. Um, let's see. You know what? I'm actually going to exit this presentation and I'm going to do a little bit of typing really quickly, just so I can show what you should do and why. Uh, let's see here. So if I can open a terminal real quick and make it big. Pencil pulled up because I did a drawing. Uh, so is this large enough? Can people see my terminal? Let's
Looks
see.
good to me.
Cool. So I'm gonna have two printfs here, and this is kind of a subtle thing. So what's going on here is that if you're just printing a single variable by itself, um, you don't want to do this first example, even though that seems like, in Python or other languages, you could just do like, whatever its print function is and then a variable name, and that's fine. A lot of those languages don't necessarily use format strings, or you're not using format strings to do that. In C, you do use format strings, in this case at least. And this is bad because it'll actually work, TM. It'll work up until you pass it a string that looks like that string itself has a format string, and then it won't work. Um, this bottom example, and this is because of how format strings actually work at a low level. So, and I'll try to summarize this pretty quickly. How format strings work is the format string itself is stored on the stack, and usually the string that you're printing from. So the format string itself is stored on the stack. And when printf is called, it looks for the first thing it looks, and after that it looks for the actual like pointer to the string that you're going to print. So in this case, there's no format string, but it does have a pointer to the string it's trying to print, so it can still print the string. Here, there's a format string, so it sees the replace the %s with the contents of var1. I mean, it doesn't actually do the replace. What it says is this %s is kind of a placeholder, and go to var1 and print that. But what the implications of this are is, since the first thing it looks for is if say you set var1 equal to literally the string this is fine, and then this is not fine, that will break things, because what printf will, if you set var1 equal to this thing, but then this % and an x, or it could be %s or %, a format string itself, and there's different format strings out there that do different things. Printf will actually see this format string inside of the string and that as a format string rather than just as another character in the string. And this gets really scary when you realize that for some godforsaken reason, I don't know why, there's actually a that allows you to write to memory. And that format string like acts on a pointer, and it interprets that pointer as a place to write, and then it'll write the number of bytes currently outputted. And that might sound confusing. I'd recommend reading more on it if you want to use format. The point here is format strings are usually only used for reading data. They're used for reading a string or reading a number you want to print. But there's actually a format string that exists that allows you to write. And I mean, format strings are bad enough for format string vulnerabilities are bad enough, and that you could perform arbitrary reads with them. Now we have a way to perform arbitrary writes. You can turn a format string vulnerability into code execution, but which is pretty funny, but also pretty awful. Nice thing about format string vulnerabilities, though, is that they're really, really easy to spot in code, and so you don't really find them a lot anymore. I mean, they do exist; they prop up from time to time. There's a funny example I read about in I want to say it was not Skyrim. I think it was Oblivion or one of those games. The author of the blog post I was reading didn't exploit or didn't look hard enough to find didn't look hard enough to find like a way to exploit it, even though it was potentially exploitable. But he did find a format string where he found a way to give user input that had %signs and format strings essentially, and he would receive output that was reading memory that it shouldn't have been. And that was in the, I think, late 2000s, if I remember correctly. So they'll still pop up from time to time, but they're definitely an older vulnerability that's probably better about, for the sake of learning about it and for the sake of seeing another example of binary exploitation, rather than like something you're probably going to find in the wild. I would say these days you're better off looking for stack related vulnerabilities, heap related vulnerabilities, bugs, that sort of stuff. That's more, probably what you'll be finding out in the real world than format string vulnerabilities. So, so exploitation, uh, buffer overflows. So I've kind of beaten around the bush a little bit. A buffer overflow is just, yeah, you read too much data into a buffer. But what that really means is a buffer. All a buffer is it's just an area of memory. That's it. But it's a finite area of memory. Maybe you can increase the size or decrease the size, but at least at a certain point that buffer is a static size. And if you have a buffer that's of size 10 bytes, a 10-byte buffer, and you read 20 bytes, and then you try to store those 20 bytes in the, and then you're going to overwrite the 10 bytes after the buffer. Now that 10 bytes after the buffer might be being used being used for other purposes, but it didn't matter what they were being used for. They still got overwritten. So here, I'll draw a little picture actually here, because I find graphics are great when it comes to talking about. So we have a buffer here. We have some memory. And this is 6 bytes long. And I'm just going to make this in blue. Why not? So let's say you're writing to this 6-byte buffer, and you write in, 8 bytes to the 6-byte buffer. Possible 2 bytes is, these 2 bytes hold maybe a variable. So now you've changed a variable. That can be bad enough. Maybe those 2 bytes are a pointer. So now you've changed a pointer. Could be a pointer variable, or it could be a pointer that points to something interesting. And so now you've made that point to somewhere else. And as you'll see, a lot of binary communication is making pointers point to things that. So let's see back here. Okay, so where do I go next? So, because I think one of these slides, yeah, is this. Perfect. So as you can see, if you are able to read too much data, no, if you write too much data to a static buffer, you can corrupt memory that happens after the buffer, that occurs after the buffer, and that memory might be being used for other things, and you can maybe you can do anything from changing variable contents to overwriting pointers, and you can eventually leverage that to actually run code. And yeah, there's some functions that get a bad rap, and for good reason for this. Stir copy by itself is bad because it doesn't length check. Stir copy is a function which copies one string to another. So like, let's say you have let's say you have a string that's not full yet in C. You have an array, a character array that you've allocated some space for, a character array, and you want to copy an existing string over. Stir copy will do that, but it doesn't length check. So stir copy would let you copy 20 bytes, of data to a 10-byte buffer, and it will do it for you. It'll just correct 10 bytes past it in the process. So stir copy's bad. Don't use it. Use stir in copy. I think some people don't even like that. So there's actually there's other versions of the function as well. Stir in copy takes a length as well, but then you have to make sure you're using the correct length. And then gets, of course, is like the mother of all bad functions. I mean, gets is such a bad function. When you run I'm sorry, I have to do this is just such a meme. You run man and that's not it at all. It's got to be 3. There we go. Yeah, okay. Man 3 gets and you read about the gets function. So the first line, deprecated. Okay, there's a lot of deprecated stuff, but it's deprecated. And then in the description it says no check for buffer overrun, see bugs below. So it encourages you to look at the bugs in the description. And then in the return value, in the description, the return value, there's buffer overruns and the fact that there's no checking. So they're not selling you on this function by. And then in the bugs, the first sentence is never use gets. Like, don't use this function. It exists, you can use it, but because it is the man page essentially just tells you how this function is. And the reason why is because gets reads from standard in, and it writes whatever it receives to wherever you point it to. So like, let's see, am I gonna do this? Yeah, I'll do some live coding. This will take me literally 2 minutes. So we're gonna let's see, is that, I always second guess myself when like live coding here. So I'm gonna make a character array. I'm gonna call this input, and I'm gonna give it 16 bytes. Yeah, we'll say 16, and then I'm gonna do a little printf. You know, type in some input, and I'm gonna do another printf just to. This is essentially just gonna be like an program that just echoes out whatever. And actually, oh, I'm gonna do something with this. I'm gonna use this as an opportunity to demonstrate both format string attacks and why gets is bad. So, yeah, I'll do that. Hopefully I'm not embarrassing myself, you know, too hard here. What? Oh, yeah, sorry. Yeah, I am definitely embarrassing myself. Too much scripting. Pound sign exclamation point. Yeah, shebangs don't belong in C code. Force of habit. Okay, so yeah, if you the funny thing about using like say literally just using the function gets will get you a warning because it's bad. The gets function, literally the compiler tells you the gets function is but then it'll go ahead and compile the code anyway. So actually I'm gonna, oh wow. Okay, so very organized. This is what I have a temporary directory for. So so it'll still compile though. Like it'll still like we still have an executable, and if we run it, you know, we can give it some input, and it'll output. But we can also pass it. Let's say, actually, hold on. So here's our source code again, just for reference. And if we run this, you'll note, you know, again, we only have 16 bytes of input. So if we give it more than 16 bytes, so, you know, that's 16. Let's give it 18. No, let's give it 20. Let's give it 24 to be safe. I mean, that's way more than 16. If you give it a lot more than that, it'll break. Yeah, there we go. So it'll actually, in this case, it could detect that we were overwriting. Actually, in this case, I think it might have already added stat cookies in by default. Yeah. So by default, by default your compiler has a couple of security checks enabled later, but those are actually compiled in, and they actually detected that I was writing too much data in. So, and you might be thinking, wait, why didn't it break when I A's, even though I only allocated 16? Sometimes that actually happens. Sometimes you need 28 instead of 24, or 30 instead of 24. You need more, because even though in the code you might have allocated 16 bytes, really the compiler allocated 20 or 22. And then on top of that, there might be some variables afterwards that you can overwrite that don't actually. In this case, there aren't, but maybe there are. Or you can I mean, there could be other weird stuff going on. So it might look like you have to write more than 16, but in reality, it's 16 bytes. You might have to pass it a bit more than 16 bytes before it'll crash. Uh, but yeah, so that's how that works. And yeah, that's because gits doesn't length check. It'll just keep writing to as long as you type in writing. That's how the function works. So, okay, so let's see here. Stack frames. This is where we start getting into like really how binary exploitation works. A stack-based binary exploitation. So in order to do stuff with that, you have to understand stack frames. So just you have this area of memory called the stack, and it's used to store data. And that data is usually like local variable inside, maybe depending. And other data includes return addresses and this previous base pointer that I'm not going to talk because it's not actually as important right now. But how it's organized is that every single function gets its own stack frame. So if we have, say, actually, I'm just gonna use the pen anyway. That'll be fine. There we go. So ignoring this, let's say we, here's our stack. And we have a function, int main. And then we have a function, let's call it func. Why not? Each of these functions is going to I mean, this is just example code, so I know it doesn't matter. Each of these functions is going to have a stack, and the stack frame is going to be created right before, well, part of it's going to be created right before the function gets called, and then at the beginning of the function call, the stack frame will pretty much be finished, having been made. So you can almost map this out as, main gets a stack frame. Well, ideally I would have drawn func above main, but it doesn't really matter in this case. Main. So this is kind of like the main function's scratch pad for main. So if you're dealing with local variables, or depending on your calling conventions, maybe you're also dealing with function arguments, but that depends. But local variables for sure are dealt with on the stack and inside of that function's stack frame. And then immediately above, I know graphically it looks like it's below, but I'm drawing it, but I'm going to call it above. I could make the excuse that that's because on Intel systems, stack grows down, so like the top of the stack's actually below. And I could say that that's why I did this rather than because I happen to draw a func below main, but I mean, it doesn't really matter. Func's stack frame is here. And information on the stack frames. These stack frames have the local variables. They have the saved base pointer, which exists, and it's important to know, but not important enough for me to explain because that would take me a lot more time. And this thing called the return address. And this has already been drawn out in the slides much better than now. Back. So actually, the only issue I have here is that this part of oh wait, no, never mind. I take that back. So we have kind of a diagram here, and main has its own stack frame that looks kind of like func's stack frame, but is more specific to main, and it's not expanded. Here we've kind of expanded. Here we've kind of expanded func's stack frame to look at the contents of the inside. So we'll see we have local variables. We only have one local variable, and that's this buffer. So that gets space on the stack frame. Then we have the base pointer. and then we have the return address. Now the return address is key because it's just a pointer that tells you where to return back to. So in this example, if you can see my mouse cursor at all, the code execution looks like this. We call main runs, it calls func, it jumps up here, and it runs it runs this line which allocates 16 bytes. It runs gets, and then it returns. But how does the func function know where to go back to? How does it know where to return back to? The answer to that question is the return address. Well, the place where to return to is stored on the stack. The return address here points to this next line, return 1. It points there so that once func finishes executing, it takes this return address and it takes that return address and it says go there, and then it goes there. But it takes that return address that's on a stack. So if you change that address, you can change where the program returns to, and you can make it return somewhere other than return 1. Maybe there's some code that you can't, that maybe there's some code that doesn't exist in these 8 lines, but that you could jump to instead, and you want it to jump there. Or maybe you've placed code in memory and you want it to jump to your code in memory, and your code is like essentially shell code, or it could be malicious code, or it could do something interesting. So if you can, this is an example where you can turn buffer over by overflowing this buffer on the stack, overwriting the previous base pointer, and then finally overflowing into the return address and corrupting that. And by corrupting that and changing it, you can make it point to anywhere. You can make the next piece of code that gets executed, anywhere else or anything else, theoretically. So, so that's kind of how that works. You can also think of it as this return address is essentially just a stored EIP or RIP for 64-bit systems. And what really happens is that when a function call exits, this return address gets popped, into EIP or popped into RIP. So you can think about it that way too, and that's so. So yeah, we can overwrite local variables as we see if there are more of them than just this one buffer, and we can overwrite the return address. And overwriting the return address. So yeah, as I said, let's say you have some code that does something interesting, like in our case gives us a shell, runs binsh, and you have that code somewhere in memory, and you know where that code is in memory. You can overwrite the return address to point to that code. You'll get a shell, and you get control. And you've turned a simple program. You've turned a simple program that just echoes your name in. Kind of like my gets example. You can turn that into running like arbitrary code execution. Now, this works just as I've described. 15 years ago. 15 years ago is an understatement. I would say more like 22 years ago. Smashing the Stack for Fun and Profit by Aleph One was published in Frac around, it was either 1993 or 1996, I think. So that was the mid 90s. And since then we've developed some security mechanisms, but I would say those security mechanisms really started being more widely deployed and like existing really by like the early to mid 2000s. So so for a while now, it's not just as simple as overwrite EIP and you win. You might have to do some extra steps to bypass this security mechanism, which I'll talk about in a sec. But yeah, and here I guess this is just the idea, is that this red is the attacker corrupting memory, corrupting the local variables in the base pointer and the return address, and you can change that. Actually, you could go a step further, and if you wanted, write as much memory as you want, or if you can just overwrite enough memory, you could potentially corrupt main stack frame too, and you can do stuff with that. This is when you can start to get creative. Returning to programming. So what I've just now described is like a building block to return-oriented programming. Your classic example, like, Aleph 1's smashing the stack for fun and profit, your classic example did something like this, and I have to draw another picture. If we your classic example of like stack-based buffer exploitation, like, yeah, I'll draw it vertically. So you have a vulnerable function. I'm going to call it vuln, and it gets, you know, a stack frame here. It would have done something like this. You have a buffer you can overwrite, like a local variable that's like an array or something like that. You have your saved base pointer, which we don't care about right now. There are I keep saying we don't care about it. The saved base pointer, or frame pointer if you prefer, is actually important. It's worth knowing about, and you can actually use it in exploitation. Um, but it would just be extra stuff for me to explain right now. But it's worth looking into later if you want to learn more about this stuff. Um, and then you have, of course, the saved return address, and how classic, like, this is kind of like stack buffer overflow to shellcode. This is kind of where shellcode comes into play. How that would work is, you can write to this buffer, but there's a buffer overflow buffer, and what you really do is you corrupt it with your data, and you overwrite the buffer, you overwrite saved EBP, and then you overwrite ret, and you overwrite it with a value specifically that points to. I'm going to overwrite it with a pointer that points to here. You might be thinking, well, what's here? Well, you can keep overwriting. So what you're going to do is you're going to overwrite this area of memory with your malicious shell. Well, it doesn't have to be malicious, I guess. But I guess the idea is if you're exploiting a program, I mean, yeah, I guess we can say malicious, and that's in this case. We're assuming the program doesn't want you to do this. So what happens here is you're actually using your shellcode as input, you know. So like you're able to send, you know, input which gets stored on the stack, but you're able to send too much input, and a part of your input is actually shellcode. Shellcode is just machine code. That's it. It's a bunch of bytes that those bytes can be interpreted by the CPU and run, you know, as machine code. And what you're doing here is you're overwriting the return. Well, what you're doing here is you're overwriting the return address to point to the next line of your input, which is actually just this shellcode. And that's a very classic attack, but there's security mechanisms in place to prevent you from doing this exactly as I've just described. But that's worth knowing about because this is nice. You can execute whatever code you want. You could have this malicious, you know, shell code pop a shell. You could have it run binsh. You can also just have it do other things besides running a shell. Um, uh, you could have it really do anything that you can do with this. You could have it run a fork. I mean, literally, like the world is your oyster at this point. You could have it write a file. You could have it open up a network port. You could have it do anything. So this gives you a lot of control, a lot of flexibility. Assuming there aren't other limitations like how much data, and that sort of thing. But back to the presentation here. We have return-oriented programming. And actually, before I talk about return-oriented, I'm going to skip around just a little bit because we need to talk about mitigations. And the reason we need to talk about mitigations is because return-oriented programming defeats some of these mitigations. So the first mitigation is we have ASLR. So at one point in time, you know, we had virtual addresses, but essentially when a program was loaded into memory, it was going to be loaded at the same memory address every single time you ran the program. So you always knew where things were going to be in memory. You always knew that these variables were going to be at these, that the stack was going to be at this memory location. Always knew where things were going to be. And that was great for exploit writers because they could just, you know, write exploits with hard-coded memory addresses and win. So a simple way to kind of defeat this is you randomize where things are loaded. So when you run a program, all of a sudden the stack is now located at a slightly different place in memory. It might be in the same general area, but it's going to be 100 or 1,000 or tens of thousands or 100,000 bytes above or below where it was last time, and you can't predict where it's going to be because it's random. So you can no longer hard code addresses into uh, because the stack's going to be at a random location. The heap's going to be at a random location too. So if you're doing heap exploitations, and in many cases with ASLR, you'll have the stacks randomized, the heaps randomized, but the program itself is not randomized. So memory addresses within the text section within like the code itself will still be the same every time. But with position independent code, you actually you can also have there are ways you can have executables like with position independent code where even like the program itself, even the code is loaded at random memory addresses each time. So that's something that you can turn off or turn on. But with ASLR, at the very least, if not more than this, at the very least, usually you have the stack and the heap. So that makes things a lot harder because you can't predict where things are going to be. Not impossible, but that's harder. One way you can defeat ASLR during program runtime, if you can leak a memory address and like figure out where something is, you can at that point, like with ASLR, since you don't know where things are, since they're randomly, one way to defeat this would be to get a memory, an address, and you know that this address is located at this in the stack or this offset in the heap, and if you leak that memory address, all of a sudden, you now kind of know where things are. So you have to find an address. A problem of not just exploiting the program, but finding an address leak and then finding a way to. So that's one way you can defeat ASLR, but it does make things harder, much harder actually. Let's see here. DEP. Okay, so data execution prevention. Also called NX. This is actually a bit in your and there are ways to do this without like. So you have a hardware bit built in your CPU, although there are ways of doing this. Support for it, but essentially that says certain areas of memory are executable and certain areas of memory are not executable, but it enforces that. So part of the problem with this example here was we overwrite a buffer on the stack, right? And again, this is the, let me get my pen here. This is the stack. The stack is just a section of memory, like any other section, but it's far away from where code is actually executing. You want to go down, let me think, go down about like 1 billion or 2 bytes, like, way, 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 way down, and you'll get to a completely different section of code that's somewhere else in memory. And this is actually where Vuln's code is. So, the code that Vuln that executes inside of Vuln is located here. The data that code uses, or at least most of that data, the local variables and like other stuff, is going to be located here on the stack. This example is kind of sketch because when you think about it, we're running code in a place, in an area of memory that's only really used for data, or that should. So it really doesn't make sense that we should be able to execute anything on the stack. Like, the stack is just a section of memory used for data. Why can we even run code there in the first place? And so NX's answer to that, or DEP's answer to that, is you shouldn't be able to, so let's just not. And so you can mark the stack as non-executable, and then even if you do this, even if you have a buffer overflow, and you can do this, this code won't execute, because the moment you try to execute this code, there'll be like an error, there'll be an interrupt, and you'll get an exception. It won't work. So, and there's let's see here. What was I gonna say? And you can implement this with paging, and you can implement it with hardware support, as well. And yeah, So this can also be referred to as write XOR execute. And so, or actually, I think write XOR execute is like an extension of this, where you have sections of memory that you can write to and sections of memory, but they're never the same. So you'll never have a section of memory that you can both at the same time write to and execute from. Uh, that, of course, causes problems because you need to write code into memory at some point in time. So what you usually do is you map memory as writable, you write your code to it, and then you say this memory is no longer writable, but now I'm going to map it as executable. So they're never the same. They're never writable and, and executable at the same time. So yeah, this breaks a lot of stuff too. And we have stack canaries, which are referred to way earlier in the presentation. So the idea behind a stack canary is in your stack frame, you put a special variable, a special value before the return address or before the base pointer, either way. The idea is if you overflow a buffer and you corrupt all the way up to the return address, you're also going to corrupt the stack canary. Like, you overflow to the return address, you corrupt the stack canary, and the stack canary is now different. So there's some check in the program that says, hey, if the stack canary is different, halt the program because there's some corruption that should not have occurred. Whether it was an attacker and an exploit, or maybe it was just a buggy program that that overrode its own stack because of a bug. So so stack canaries, and the idea is a stack canary is going to be random. So like every time you run or different stack canaries that are placed on stack frames in the program, and they're hard to predict. So some ways you can attack stack canaries is trying to predict them, but that can be hard. So let's say you can't do that. Again, this is where an arbitrary read might be useful. Where if you can read from memory, but like you perform an arbitrary read, maybe you can read stack canaries and you can incorporate that into your exploit where you say, I got this arbitrary read. I can read this value in memory. Now I know the value of the stack canary, and I can continue to overflow this buffer and just overflow the stack canary with the right value. But if you don't have that, or if you don't do that, this will break stack because you're gonna overwrite this canary if you're overflowing from local variables to the return address. So these three mitigations are problematic. ROP breaks two of them completely, and ASLR somewhat. ROP helps with ASLR. ASLR is still a problem when you're doing return-oriented programming, but in some ways it becomes less of a problem. However, it does completely destroy dep and stack canaries because return-oriented programming, you can think of it as the program playing "Why are you hitting yourself?" What really happens here is you're overwriting the stack with. Wait a second, let me exit this because I'll draw another picture. What you're really doing here is you're overwriting the stack with a bunch of fake stack frames that point to different parts of the program, and you're causing different parts of that program to execute in any order that you want. So you have, main. I'm not even gonna worry about syntax here. And you have main's code, and you have like a function, and you have its code, and then you have maybe you have a function that's like read file, and you have its code, and you have some other functions, and you have their own code. So you have let's say this is the body of a program, and this is its code. So if we have this example of the stack again, and you have a buffer overflow, what you can do is you create a fake stack frame. Actually, I'm going to do this in red. You create a fake stack frame, and you have the stack frame point to any arbitrary section of memory. Maybe we have it point to read file, and we get that bit to execute. And then the idea is eventually this is going to return, and when it returns, it's going to use the next stack frame, which we can also made another, and that points to maybe func. Okay, cool. So then func returns, and when it returns, it goes, it goes to the next stack frame, which we've also written. So if we create, 3 fake stack frames. We can have these stack frames point to wherever we want, and actually, we don't even just have to point to functions. We can point to in the middle of functions. So we could have this fake stack frame or to like the last couple of instructions, and if those instructions happen to do anything useful, then even better. So at this point, overwriting. Notice there's no shellcode with these stack frames. There's no shellcode. This is just we're making a fake stack frame, some fake maybe some fake variables, but usually not even that. Fake arguments if arguments are passed on the stack. Sometimes they are, sometimes they're not. We have like a fake return address. And okay, well that's a bit messy, but anyways, the point here is each of these stack frames is going to have like optional arguments and a return address, and this return address is going to point to somewhere, some other section of code. So the idea is, since every function gets its own stack frame, and when a function is done executing, you go to the previous stack frame, you can make a bunch of fake previous stack frames, and you can cause code that already exists in the program. You're not writing new, causing code that already exists in the program to execute in any order that you want, like an arbitrary order that's determined by the stack frames that you create. And so then it just becomes a matter of what sections of existing code are actually used and what sections can I leverage to perform some action that I want. And so that's where in these sections of code that you leverage, these sections of code that you take advantage of, that you create fake stack frames to point to, those are called gadgets. And a gadget is any sequence of code that ends in, it's any sequence of code with one or more instructions ending in a return. And that return is key because that return will, quote unquote, return to the next function and place you in that next stack frame with its own return address. So yeah, return-oriented programming is cool. You're not actually writing code to the stack. You're just writing a bunch of stack frames and here, yeah, you don't even have to overwrite return. You can really just create a bunch of fake stack frames and not worry if you're writing exactly perfectly, as long as those stack frames look, and as long as they kind of work out in the end, sort of. But yeah. So yeah, it's return-oriented programming is just using the program's own code against itself. It's kind of a generalization of C, which is essentially just return-oriented programming, but you make it return to C library functions, which are like dynamic, like shared library functions. So the funny thing is, if you look back in history, actually, return to libc was invented first, or conceived of first, where people were returning to libc functions. And then in 2007, there's this guy who realized, hey, wait, we're returning to libc functions. Why don't we just return anywhere we want? Like, why don't we just return to any functions we want, or even in the middle of functions? And he wrote a paper about it and coined the term ROP, return-oriented programming. And you can find this paper online. It's actually well worth a read. It's a great paper with one of my favorite titles for a security white paper ever. The title of this paper is "The Geometry of Innocent Flesh Upon the Bone." Now, how metal is that? That's pretty metal, and it makes kind of a sense. Sort of return-oriented programming. The program code is the innocent flesh, and the important part of return-oriented programming is you need to take into account the program structure and what it gives you, which is its geometry. And then I guess the bone part comes into play, where it's like, the flesh sits on top of the bone. I don't know, but the title kind of makes sense, but it's and if the title's that good, that should just tell you how. And actually, yeah, I'm kind of being facetious here. The rest of the paper is very good, and it explains return-oriented programming very well, and it holds up. It's pretty cool. So we've covered mitigations, and then we've covered programming, which breaks a lot of those mitigations. And yeah, I guess that's the end of the presentation. Yeah. If anyone has any questions, I'll be happy to answer. Um, Sorry if I sounded a bit rushed or a bit uh, messy. This is my first time presenting, so I was understandably a little bit nervous.
No, you did fantastic, Mark. We appreciate you presenting, especially remotely. Next semester, you'll get a lanyard for presenting. Um,
Oh, thanks.
does anyone in Twitch or Discord have questions for Mark before we let him go? We're gonna give him a minute to go through because I know the stream's a little delayed. No, but you did fantastic with the short notice, and you went through everything extremely thoroughly.
Yeah, sorry. If I'd had more time, and I'd
Oh, I know there could be a class taught on each one of these things.
yeah, that's the other thing too. Is I feel bad because there's a lot of people here who already know the basics of assembly language.
Newman
Assembly.
gave you some claps. I'm gonna say that's it because there seems to be no questions.
Oh, okay. I'll make one other point. And I guess this is real quickly. And this is, I guess you could apply this to not just binary, really any subject. Something that I try to strive to be better at, but that's always a challenge. Is there's lots of people who come from different places of background knowledge. Some people who, aren't even, aren't very good programmers, and then, and that's fine. Is some people programming is just not their strong suit. Um, and then there's other people who